Well, this is the last section of this chapter 39, and this section is on 39.8, called a particle in a box. Well, we know classically what it would be like to have a particle in a box. We can take a box in classical physics and put a ping pong ball in it. The ping pong ball will go over here, bounce back, go back over here, bounce back over here, and it has an even probability to be in all of these places. It just bounce, 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 bounce back and forth inside this heavy box. But in quantum theory, something very different happens. When we contain a particle inside a box that has a length L, something different happens. The probability wave must end up having a node. Now here's a node, here's a node, and here's a node at exactly this side of the box and this side of the box. In other words, the probability must vanish for it to be here and vanish for it to be here. It follows that if we have a length L, then our wave is going to have, what is this? It must be a half of a wavelength, must go an integer number of times. So an integer times a wavelength over 2 has to equal to the length of the box. Now that just means that we can fit in a half that might be like something like this. From a node to a node, 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 node to another node. That would be 1, 2, 3, 4, 5, 6 half waves. Or I can have 7 half waves, but I have to have a node here and a node here. That's what this equation says. Okay, now that I've written this down, then I can solve for the wavelength. So this implies that the wavelength must be twice the length divided by an integer. An integer, n, can equal to 1, 2, 3, all the way up to infinity. We have a tremendous number of these oscillations. Well, where does this get us? Well, we know what the momentum has to be. The momentum, you recall, is Planck's constant divided by the wavelength. So now I'm going to take Planck's constant and divide by the wavelength. So I invert this and multiply. It's going to give me n times h over 2L. So now I have a momentum, P, must equal to a multiple of h over 2L. And you can notice that when n is equal to 1, that's the lowest momentum. So it's integer times the first momentum. Now that's incredible. This says that the momentum must be quantized. It is only an integer multiple times this basic value, which is the first momentum. So I can have twice that value, 3 times that value, but I can't have any other momentum in there. It will not live there in that box. Well, now that I know the momentum, assuming this is not a relativistic problem, I can compute the energy. And the energy I compute here, and it's equal to p squared over 2m. Well, that means I can take this and square it, and I would get n squared h squared over 4l squared times 2 times the mass. And if I simplify that, I get energy is equal to 2 times 4 is 8. So I would get n squared times h squared over 8m L squared. So now we see that the energy is also quantized. And it will go as multiples of the first energy. What is the first energy? E1 is where n is equal to 1. That would be h squared over 8m L squared. That's the lowest energy you can have inside a box. So you can't even have zero energy. This is called the 0 point energy, or the lowest. The lowest energy that's possible. And now we can see that all of the other energies are the square of an energy times that basic one. So the next energy is 4 times as much. And the next one would be 9 times as much. And the next one 16 times as much. So these go as the square of integers. And this gives us actually all the discrete energies for a particle in a box. Why is a particle in a box important? Anytime we take a quantum mechanical particle, like in nanoscience or anywhere else, and confine it within a certain region, it's going to have discrete momenta and discrete energies, certain energy levels. And if it loses one energy and goes to another one, it's going to give out a photon that's a difference between one energy and another one. So, for example, it could go from the nth to the nth energy level, and that would give us n squared minus m squared times this basic energy, which is h squared over 8ml squared. And you can see that the difference of these energies will be the energy for the photon. E is equal to h times the frequency. So you could actually use this to compute what the frequency would be of photons that were given off as the particle jumped from one energy level to another.